I want to welcome everybody to our third night of our education sessions. And we have a full slate tonight. We have actually 3 of them going, but we are being kicked off with Brian Pruitt from Intel, who's going to tell us a little bit about the Intel RealSense cameras that we have available for our hackathon. So with that, Brian, take it away.
Fantastic. Where I thought I would start with this is minimizing this. I'm going to give you an overview of just depth in whole, and then at the very end of this, I'll talk about our products in a little bit more detail. But I'm really going to focus this whole presentation on why we are in this whole 3D market right now. So if you think about RealSense, what we have done is we have moved in the last 11 years to figure out how to give our devices the ability to see. We really want them to understand and interact with the entire environment. If you look at the explosion of IoT over the last 10, 15 years, who would have thought that every device would need a processor? Like, why would you put a processor inside of a doorbell, for example? So what we've done is we've expounded on that and said, look, as devices evolve for the future, they'll want to do more things, and to do more things, they need to be able to dynamically interact with their environment. One way we do that is through computer vision. I wonder. Okay, whatever. The way that we do this is we first look at how we interact with the devices in our environment. So your eyes are a great starting point for us, and then you use your eyes. They're essentially like 2 imagers, and then your brain does all of the calculations to understand depth. That's why if I take an object like my camera, I put it here, I can say, oh, this is about, 2 feet in front of my face, or maybe 1.5 feet. But when I start putting it 100 yards away, I'm going to have a greater error rate there, just because my calculations may not be as good as somebody else's. So what we do is we start looking at the problem. There are a ton of 2D images out there, and you will see a lot of folks out there that are talking about using 2D with AI. AI is such a magical term, but so many things use AI today. One is, why do I need a 3D camera? Why can't I just use a 2D camera? And I love this picture in that it shows you something up close and something very far. With a depth camera, there's no doubt that things are very far, because my camera's telling me for every pixel on the screen, I'm getting a depth, or I'm getting a range to that pixel. So there's no guessing, it's just how accurate is that depth information I'm getting. If you're using 2D and AR, you have to have some kind of reference. You have to have some kind of training done. So for example, I would have had to train my AI model on the mounts here and say, okay, I need to estimate that a mount in the foreground is X amount of meters. And based on that, I can extrapolate using a bunch of different learnings in AI on distances in this photo. And then it's an extrapolation, so it all depends on how well it was trained and how much computation you're throwing at it to be able to get that. It's a huge difference between being able to do that for thousands of dollars with the compute and the time and training behind it versus $150, $160 depth camera that gives you this information. So we want our camera to not only see this 2D picture, but we want it to understand the distance, just like we do in the real world. This opens up so many different avenues. So if you look at what we're trying to do, is we're trying to give you a color picture like any 2D camera. We're giving you the depth data, and we also throw in an IMU just for motion. So it's really important that whatever device is utilizing this, they are making use of all this extra data to do whatever the case may be. In the example below, it's a recreation of a section in our office space. And this takes a lot of time if you're actually having to draw it out to scale and understanding all these distances. Whereas all we did is we ran a robot actually looking to the right down this path, and you can see where it took a map of this. So for us, it took, I don't know, maybe a minute. But if you had to use software and conventional means to understand what all these distances and lengths are, you would take much longer than that. What does even the depth image mean? Well, what we do is each pixel in a 2D camera has a color value, an RGB. Everybody understands RGB. So the red's red, the browns are brown, the blacks are black. What we do with depth, and what we call a depth image, is not only do we take all of those pixels, we take those pixels and we go to the subpixel level, and we figure out the depth of those subpixels. And then when we align it to a pixel, we have like an averaging formula that says this pixel, based on the 2 or 3 subpixels around it, give us a depth value. And so for every pixel you see on the screen that runs at 30 frames per second, we're giving you a 30 frames per second real-time depth image to go behind it. So you get both of these data. I stress on the importance of the 3D camera is the amount of extra data I'm giving you. It allows you to open up your mind, and if you're doing a robotics problem, now you have the capability of understanding that turn is coming in 1.245 meters, and I need to do X when I see a turn. Or the field dynamically changes. Somebody stepped in front of my robot. My robot has a braking capability of 0.3 meters. I need to know how much I need to slow down before I run into this person. So in a dynamic changing environment, it's even better because you have all of the capabilities to interpret the environment in the way that you want. Now, what happens is we start talking about this idea of good depth. And if I go back to your eyes, you may be able to judge how far this distance is better than I can. But you want conciseness. You want it to be an exact number. You want the true data. So what does it really mean to get those good depth pixels? Well, there are many ways of doing it. And everybody wants, perfect depth at $5. And that's just not going to happen. You have to do trade-offs. I love the example of you put a big Velodyne laser on top of a car, you put a ton of power through it, you make it very directed, you pulse it, and you set the right frequencies, and you're able to get a good signal back for what you're doing at the speed that you needed to go for. But you're not going to do that for $100. It's going to cost you more money. So what we do is when we designed our cameras, we said, we're not going to play in the $10,000 market. We're not going to play in the $1,000 market. Those are very expensive, very directed, focused 3D cameras. What we're trying to do here is we are looking for the everyday type of device. And that's a little misnomer, but we're looking at the robots that are looking for things like collision avoidance. Now, if I'm doing a collision avoidance, and these are my two objects, I don't care if the object looks like this or if it looks like this. The noise, I don't care how much noise it is. So if my object is here, and I know I'm showing it on a 2D camera, but I'm trying to show you your spacing. If my spacing's this far apart, it's not going to matter all that much, because if I see it 5, 6, 7, 8 meters away, I'm going to start figuring out what I need to do to avoid it. Now, as I get closer, my stereo cameras like this will get more and more accurate, getting down from, when you're out at 30 meters, it'll be plus or minus 5 meters. When you're at 20 meters, it'll be plus or minus 2 meters. If you're down to 10 meters, it'll be plus or minus a meter. You're down to 2 meters, it's plus or minus centimeters, and then so on and so forth. What we do is we build cameras for each of these situations. So for example, collision avoidance, a low-cost way of emulating what we're doing is taking 2 cameras and running an algorithm on here, and you get a pretty good depth map. Scanning, you may want to do something a little more high res. there are different ways of doing that, and you can go over the scene a number of times. So if I take another object on my desk, you get to see my Starbucks cup. If I wanted to make a perfect Starbucks cup in a 3D space, a digital twin, I could go around it like 3 times and just average all of the dots together, or all of the depth points, and get a real good picture. But we also make another camera that's based on LiDAR, this very concise, very specific thing. And I can do it in one scan, or a scan that's above the view and going downward. And so that's why we do another camera. Hand tracking, you want the good edges and you want a good fill rate. If I'm trying to track my hand, I want to see my extended fingers and where they're at. I need to be able to tell if there's differences between the fingers, and I need to be able to see when they occlude each other, how it tracks. And then perfect tracking, all I need to do is see the core. I don't need to be able to tell that I have 5 fingers. I need to see that I have a core, and then I can track that person. So the depth model is very important. So use case is very important, not to override what you need for perfect depth. You need good enough for your machine or your use case, so that you're not spending $10,000 to get down to the micrometer. You're spending $150 to get down to the centimeter. So very big trade-offs here. So how did we approach it? We did it very many different ways. So there are different types of depth sensing techniques. And it's not like we created these. They've been around for years and years. All we did is we added our own flavor to them. So we're using optical for one. You can use other things. You could use sound. For example, like a lot of vacuum cleaners will use an ultrasonic sensor. But once you start talking about optical, you start talking about active and passive. Am I going to send out a signal and measure that signal, either the distortion of that signal, or am I going to do some kind of triangulation, or am I just measuring the time it takes for that signal to go there and back? That's these structured light, active stereo, and these coded light pieces. And you're familiar with the Connect. If you haven't seen our site, I'll show you our website here in a little while. But this is exactly the type of technology that we tackle. There's also the time of flight, and this is where our LiDAR comes in. It's the time it takes the laser to shoot out and come back, and we measure it. And this is what Velodyne does also. And then there's the phase shift and the you get it, the IC laser. It's our other laser that we use with Mobileye. And then we also have passive stereo, which is the same as our eyes. It works the same way. And if the best way to explain it is if you take your thumb and you stick it all the way out, you close one eye, close the other eye, you see a little shift here. This is how the passive works. I'll talk about that in a second. But the stuff in the white are the things that we have designed in-house, and we put our own flavor on it. The real magic behind this is how we've manufactured this device, and that we put our own ASIC inside of it that do the depth calculations. It doesn't do any other processing. It just makes that RGBD depth data all come out of the same USB connection that we have on the side here. So you're not using this heavy AI, you're not using this high-end GPU processor to do these calculations. It's all done on a very targeted ASIC. If we start getting into the different versions, you have stereoscopic right here. Stereoscopic is, like I was explaining before, it works just like your eyes do. And if you look at this, our 2 sensors, if I put them up to my eyes, may be about the same distance as my eyes. That's where we started for our first distances. 50 millimeters and 55 millimeters are the 2 different D415 and D455. What happens is, if you look in the picture, this is a picture from our left and our right imagers, the 2 imagers on each of the side here. Or if you're looking at the picture, the 2 imagers on the farthest out piece. What we do is we take those pictures and we look for the disparity shift. And you can see the little picture of Yoda back there, baby Yoda. or iota, and you can see, even though this is the exact same picture at the exact same time, there's a shift. Because of that shift, there's a mathematical formula that we can do, and we can calculate a depth for that specific pixel. And we match pixel to pixel across each of the images. We use our left imager as our reference picture, and then the right imager as our target. And it doesn't matter really which one, it's just how the formula works. But we've always decided the left imager. And we get this beautiful depth data out based on all of this, and we can go up to 90 frames per second, or if you really want to shrink down your field of view, we can go up to 300 frames per second, which allows you to get a lot of data. And this is one of the reasons why we use USB 3, trying to transmit a ton of data through the Ethernet, through Wi-Fi, through even 5G, it gets clogged up. And so we're working on other technologies that will eventually address that, like data compression, or doing a lot of processing on maybe this device and then send some pre-processed portion of our depth data. We're looking at that kind of technology. So by combining these two images on these sensors, it's really the most common way that we do this. And we have 4 cameras out today that make this happen, and you can assume that we're going to grow. Sensors baseline, the FOV, the resolution, all determines where our camera is going to work at. Alignment is a big deal, and we talk about this alignment and synchronization, or calibration in our case, all the time. A lot of our competitors out there, or other companies that are doing this, don't necessarily call out one of the weaknesses of this device. Now, because I am doing this calculation, I need to know the exact distance between these two sensors. It needs to be down, in the micron range. The more accurate it is, the better my depth data is going to be. So if I abuse this camera, if I keep beating on it, if I throw it against the wall, if I heat it up in my Arizona heat, I live in Arizona, and cool it down and heat it up and cool it down, I could get some slight movement because of the way the cameras are designed. Now, these are pretty solid, so since we totally control this, they're pretty good at resisting shock and heat and all that. But we've put in 4 different ways of doing calibrations, from a self-calibration that you would take this camera, you could even put it on your face, you tell it to calibrate, and then 2 to 3 seconds, it'll calibrate itself if it needs to. Does a health check, tells you if it's good, and then it asks you if you want to update the calibration tables. 2, we have an OEM calibration where you would take a big target screen that we know the size of the screen, we know the exact distance, we know the target itself, and you're able to feed in the right parameters to update the camera. But calibration is important. If you keep these calibrated and you make it easy to calibrate, these are really concise cameras at a very low price. Now, the other part that I'll plug my camera in a little bit, but the other part is the whole idea of occlusion. So if I take an object like this flashlight and I put it in front of my camera, it occludes this piece. So there's no way I'm going to get depth on this camera if there's something in front of it. I can't see it. It's just like your eyes. I can't see it. But I can make some assumptions about the pieces behind. But what we do today is we show it as a black space, a space where you're not getting any data. And that's something that's possible that you have to deal with. And stereo is very important as it matches features in both left and right. So it's important to have texture. It's important to be able to distinguish, the picture on the left, which pixel is which pixel. We also, another point that I didn't really talk about much is, you can see on this camera, there's like another imager right here. It looks like an imager. It's actually an emitter. It's an infrared emitter. Now, this camera doesn't need any infrared sensor to work. It works as a passive camera, just like any other camera out there. But what we've done to add some extra capability to it to work in near darkness or in darkness, or on a surface like this box where you see the white piece, it's hard to tell one pixel from the other. What happens is, if I'm trying to compare an exact pixel, I can't see that pixel because I don't know which one it is. So what I do is I throw some infrared random dots here, and those infrared dots allow me to have a reference, and I can match up dot for dot a lot easier, and I'll get depth image from it. So we use active to enhance our capability, but it's not needed. We have an active passive stereoscopic camera, if you look at it that way. IR using coded light. We had a camera SR305 that we launched. It's right here. We just end of life this camera this year. Mainly, we had one customer that just loved these cameras so much that they bought every one that we had. And so what we did is, with this camera, we eventually went over to the LiDAR because we thought the LiDAR was providing a better image at a longer distance than this. But the concept is good to know. It sends out a projected pattern or a coded pattern. With this pattern, I'm able to read it, and then I'm able to see the reflected pattern, and then I can calculate the depth by the distortion of the pattern. This is very common. There's a lot of coded light cameras out there. Your phone works, your iPhone works similar to that when it's trying to do the facial or the facial authentication over here. Key points, efficient illumination, yeah. So the key points here are, the great thing about coded light is it's really concise in a short range. The bad thing is bright lights or things that absorb infrared or other infrared light going into it messes up to be able to see that distortion. Now, going back to my stereo camera, I don't care how many cameras are looking at the scene. I'm not reliant on some signal coming back here. I'm just looking at the picture. Unlike my coded light camera, I need to see my picture that I sent out there, my infrared coded signal, and I need to be able to detect the distortions. If you interrupt that with your own camera or another infrared light, I won't be able to get an accurate picture of it. So you can only use one camera per scene, unlike stereo. And then we have the phase shift, where you're sending the signal out, you're seeing a shift in the time it takes for the module to come back, and you're able to calculate this step. Now, this is what Connect does compared to us. We did not go this route with our camera, but this is what this indirect time of flight is another good way of doing this. It's to really make this work far, the really key point to talk here is using, you need a lot of power to make this work really well. And you could also do things like use what Connect does is they use like an audio type of cable, and they use it to prevent crosstalk between multiple systems. So they're allowed to say, hey, I have this camera going in here, I have this camera going in here, and they're able to work together to minimize this interference. And that's how they do it. Now, what we went to after our coded light is we went after our LiDAR camera. And the way we really make this work is we take our LiDAR camera, we take a 2D MEMS, and we shine a light on it, and we make it go up and down, kind of a scan up and down. It's like your TV that would do it left and right, but we do it up and down, and we're able to complete a complete depth map. Why is our LiDAR different? Well, most LiDARs out there, they're looking at either a single line, a single pixel line, or they're using a group of lines, or they're using a ton of power and they're pulsing it. But all of these things have advantages and disadvantages. I only have a single line. If I'm not on that single line, you're not getting any feedback. If I'm using a ton of power, I need to supply that power, and my cost is going to go up. We still want to run this off a USB, so it's less than 5 volts, it's less than 5 watts. And we want to be able to get a full depth map, a full picture of what we're seeing at 30 frames per second. And that's what we were able to do by using this custom MEMS system. Depth resolution is super good with this camera. This is our best camera at being able to provide a clean, clear picture of what's going on in the scene. And that's really our main advantage of this camera, is when you need a clean picture, like for scanning, we're moving you towards LiDAR because it can give you that cleaner picture. Now you can look at all these different technologies, and essentially what they can do is you can see the differences here. You can go up and you can say, I need X, I need depth accuracy, and then you can pick which one's going on. And these are our opinions. It aligns with the market itself. But the biggest thing that we have to do for new customers that have never used our camera is understand the idea of the way our cameras are supposed to work. One camera does not fit all use cases. You have to figure out what your use case is and then apply the right camera to it. Now, if I look about RealSense technology, we've been doing this for 11 years. So we've put out 15 or so products, and so we've learned a lot in that amount of time, and we continue to learn. One of the best things that we do is we make one SDK to work for all of our depth cameras. So the same depth camera, the same SDK that runs this camera, runs my LiDAR camera, will run my next generation camera. And this is hugely important for these customers that take 1 to 2 years to design in something. They don't want you moving this camera away and then they have to do a bunch of recoding to go make that happen. So we learned that several years ago, and now everything's supported by our 2.0. Other things that we've done is, if you look at all this tones, we try to cover a wide field of view. We introduced this idea of ideal depth. Now, a depth camera, and I'll show you it here in a second, a depth camera can essentially see as far as your eyes can see, but it's all about accuracy to the camera's point. But what we do is we introduce this ideal range, which is where you're going to get the best data for that distance. Now, am I saying at 3.1 meters you're not going to get good data? No, I'm saying this camera's designed to work about 50 centimeters to 2 meters, where you're going to hit every one of our KPIs. After 2 meters, you're going to start seeing an error rate, and it goes up quadratically. And so at 3 meters, it's still pretty good. At 4 meters, it may be a little bit higher than what you would want for your application. And we're always conservative. You can clearly, we have use cases that are using this on drones that are seeing 25, 30 meters, and they're trying to see, oh, that's a tree over there, so I need to take some action. They don't care if it's 20 meters or 25 meters. They know they need to start moving left or right. And so as they get closer, they get better data. So it comes down to these ideal ranges of where the pattern's at. Now, I talked a ton about the different technologies. Now, what's really interesting here is the way we approached all of these technologies is we've come out into really 3 main tracks. One being our LiDAR track, and we have one LiDAR camera out today. You can assume we'll have more in the future. We have these 4 stereo cameras, and you can also assume that we're going to come up with more cameras to fill out those ideal ranges that I was talking about. I didn't really talk too much about facial authentication or tracking. These are other areas that we are exploring. Tracking kind of goes along with depth, because if you think of a robot wanting to know where it's at in a map, one of the hardest things to do is to get a robot to start here, make it go 10,000 meters, and then end at the exact same point where it started. You would think that that would be an easy problem to do, but if your robot is changing direction or distances, you have wheel odometry, you have IMU, there still needs to be other ways of doing it. GPS is only so good, and it only works in If you're indoors too much, you won't get a great signal. And being super concise down to, the centimeter or something, you need more. And this is a way of doing what we call visual slam. And we do it with this camera. It was more targeted for AR/VR when the AR/VR boom was going on. So the room size is sort of limited with this. We couldn't run it in a warehouse, but it could do an office space. And then, of course, we take two approaches when we approach the camera piece. We have the peripheral itself, and then if you don't want the whole peripheral, you can go down to an embedded model, a module plus the ASIC board, the board that is the brains of the camera. This is all of the sensors, the emitter, the RGB, the two depth cameras, and then the board itself has the ASIC card, the USB connection piece, and you put them together with a little interposer cable, and you get the same thing as the peripheral above it. So that was a ton right there. So let me do one more interesting thing.
Brian, I was going to say, not to interrupt or break your flow, but just so you know, if you could go, I don't know, you just changed that screen. Just to let you know, we have, for this hackathon, the two cameras we have are the LiDAR 515 and the depth 415. Yep. So those are the two that we are working with specifically for this.
Fantastic. I will show you the 435, which is very similar to the 415. It just has a wider field of view. So this is a very simplistic app. What this app is, it's a viewer. It's a way of interpreting depth data if I don't close it. So this is how you can tell that we're working. No, I don't want you to update remind me later. It's not due firmware right now. So this is a really quick download. It's very simple. It starts up like this. I've just plugged my camera into the computer. I turn on my RGB. This is just like any RGB. Maybe I should hold it not upside down. One of my favorite pictures are, I'm a map guy. I like to collect maps, so I put them in my office because my wife maybe not share my hobby of collecting old maps. So I can turn off the RGB. I can turn it on. I can turn on the stereo camera. So now the way that we portray stereo is we give it a color heat map, kind of like what you would see on a thermal piece. But each one of these colors represents a different amount of distance. And you can see if I go over each pixel, down in the bottom left, it's telling you how far that distance is. Now, if you want to see on the D435, as I get closer, you can make out the top of this picture. You can see the edges of it. I can move it towards my window. You can see the outdoors, and you can see I probably need to clean that window. You can see my curtains. If I'm too close, you can see what happens. I need to back up. You can see my big, thick windows, my big, thick cloth there to keep out the sun. And then I can even show my maps on the back wall here and show you all the different pieces, how far I can see. And you can see that that is trending to be, 2.7 meters away for each pixel. And you can see I'm getting data all the way across, even in the diverse lighting of my room here, all the different objects you can sort of make out. And what I have is I have another camera that would actually allow you to see this. And I have the LiDAR camera, which I'll grab here in a second. I believe I have one right available. And I can show you how the difference is, how clean it is. If you even look at my desk, there's got to be some interesting objects here, like this flashlight and my mouse. You can see my mouse showing up. You can see this. You can see that the black doesn't bother it. I don't need, black's a great absorber of light, of course. So because I'm not reliant on the light, it doesn't affect me. You can see my hands, it does a great job. But these are all points that you could use to go do something interesting. Now let me turn this off. Let me disconnect this. Let me grab my LiDAR camera, which I just had in my hand. And I want you to note that the difference in the quality there. And I'm actually using the same cable. All I did is I plugged in a different camera. You can see it recognizes it. I am going to turn on the RGB. Let's turn it up in the right direction so you can see same pictures that you saw before. Now I'm going to turn on my depth sensor. I don't care about the infrared stream. Oops. Yes. Dismiss this. I don't want to update my firmware. Obviously, I need to update my firmware. But you can see, remember how hard it was to see my frames before? With the LiDAR camera, look how crisp and clean that framing is. And you can see the differences. Like it's saying it's 0.963 meters, but if I look in the middle where it's indented some, it's 1.021 meters. So you can tell that there's a difference between the frame and the actual picture itself. You can see how crisp and clean it is for the wall here. And you can see that the black casing around my framing here, you can tell that this has a black edge to it. Now, if I point back down on my desk here, you can see how all that infrared is just absorbed by that black pad that I have. So this is one of the disadvantages of the camera. Now, if I pull it up a little bit higher, it doesn't absorb it as bad. So you can still see everything that's going on. Light's a little bit of an issue with this. So when I'm looking out the window, all the infrared from the sun is kind of washing out my sensor, but you can see the folds of my curtains a little bit more. And then if I'm looking at my back wall, you can see the distance out there and you can see that some of the light that's washing in. Now let's see what happens when I make it a little bit darker here. You can see the picture cleaned up a little bit, but I still have some light bleeding through. But you can see all of the different dots and how crisp and clean you can get these images to go through by using this time of flight or this LiDAR camera. I am going to stop there and see if there are any questions you want me to answer.
How dark the light this camera can tolerance?
The LiDAR camera, of course, can work in complete darkness because it's sending out a laser, and it only has to see the laser. The laser's an 840 nanometer laser, and it can work in complete darkness. Now, the same can be said for the stereo camera because it uses an emitter. So even though it's like a camera and in complete darkness, your camera doesn't work unless it has some way of seeing it. But I am projecting about 10,000 dots out there, 10,000 infrared dots. So I can get a depth point from each one of those dots because it can see them even in complete darkness. So the most versatile camera we have today so far is our stereo camera because it can work in the brightest sunlight. The more sunlight, the better, actually. And it can work in the darkest dark.
Yeah, I concern that the T65, for example, we use that for authentication. Is that it can be used for authentication in the dark?
So the T265 is an interesting camera. It's really used for visual SLAM. So it's really used to understand its position in space, where there is where it's at. So if I had a 265 like this, if I moved it, it knows that it moved here. It knows where it's at in respect to the map that it's on.
Yeah, it's more tracking purpose.
Yeah, it's tracking. It's a tracking camera precisely. It uses sparse depth, so it uses about, I believe it's 50 points of depth. So every time it moves, it's using 50 reference points to help with the visual slam. That's why it's so concise. And plus it uses the IMU, plus you can feed it wheel odometry, and it can use the combination of all these sensors on the Movidius chip that's on it, plus the visual slam software to come up with where it's at for location. So it's an interesting device. We haven't figured out what we're doing for the next generation of this.
Yeah, one more question. Can you elaborate a little bit about the sizing of the file that transmitting per pictures? How big the size of the data?
Yeah, if you think about a scene, so if you think about the number of pixels in a scene, there's a couple 100,000 in one frame of a picture. And so if you have all of that, plus all of that RGB information in one frame, plus you're adding a depth point for each one of those, and now you're sending that at 30 frames per second, or let's say you're sending it at 60 frames per second, you start having transmission rates that try even the best gigabit Ethernet. There's just not enough transmission, even though it says you get 500 or so meg out of it, and it's not enough. So that's why we have USB 3. Now you could run our camera on a USB 2, but you're not going to get our full resolution and our full frame rates because it just cannot handle the amount of data that we're giving real time. Now we have customers that the way they handle this is exactly what I said, is they'll go down to 5 frames per second and maybe 320 by 160 because that's all they need in the scene, and then it's easier to do. So it's one of those problems where we're trying to give you all the data that you want, but as far in advance as we're getting, sending a lot of data all of the time and reliably across any kind of distance is not a simple problem.
I see. Well, from the communication wise, we like to see a table that showing, what transmission bandwidth requirement on those things.
Yeah, sure. On our website, so we have this beautiful website.
Okay.
That I'll pull up. If you go to RealSense, IntelRealSense.com, one of the best things that we do that's a little bit different than the rest of Intel is we put every piece of documentation we have about the product, it's on here. And then we do white papers, we do webinars, we do videos and tutorials, FAQ, code samples. We put it all here for you. So one of the things you could do is you can do this white paper. You can look under D400, and you can look for some of these different modes, and they will talk to you about improving the depth, the sub-pixel linearity for our cameras. The one that you're talking about is under, I have to remember, it's actually in one of these. It might be under the camera depth testing technology or tuning your camera for best performance, but it will talk about the different resolutions and how to, this is more tuning. But you can, it's definitely in here. It's in one of these.
Okay.
We'll keep adding to these. Yeah, definitely do. If you don't find it, we can have another conversation and I'll get you the right answer.
Okay. Yeah.
Jeff had a question in chat, at least dealing with the USB 3 chipsets. I don't know if you saw that chat question. And then Joel, I didn't know if you had a question. I saw you were unmuted for a second.
I had a quick question. I may have missed the answer on it earlier on, but for the 415s and the 435s, the depth cameras, what is what's your recommendation, or what's the preferred lighting for those cameras to work in their ideal? Like if you were given a perfect situation, what would you want those to be looking at?
It's mostly texture. The lighting is whatever lighting is comfortable for your eyes. Because if you think about them, it works essentially the same way as a camera on your iPhone. So whatever lighting's good to take a picture in, it's going to be great for our camera. the more light, the better, of course. But you know, my room in here is pretty dark. I keep it dark because we get a lot of sun coming through in Arizona, and I block the sun, so this room stays dark. But the camera works really well in here, just because of that. And that's what I like about the stereo cameras. When I go out and demo a stereo camera, I don't have to ask or worry about setting up in some special spot. It just works. It works well. Now, if you go to the extremes, like total brightness where you're washing out and total darkness, I'll still work, but not as good as somewhere in the middle. And I am talking to extremes, like total darkness that's looking into the sun.
Yeah, you mentioned texture is critical. Could you spend the 30 seconds just to explain that again? I know you probably already have. I jumped in a little late, so.
Sure. No, if I look at this piece of paper, and I try to, if I take a piece of paper, sorry, I forgot I'm sharing the screen. I don't know if you can see me, but if you look at a whiteboard or a wall that's flat and it's all white, the way my stereoscopic sensors work is I'm trying to compare a pixel from the left sensor to the pixel on the right sensor. And if they look exactly the same in both of those spots, and I don't have any reference points behind them, it's hard for me to align, is that really the same pixel on both pictures?
Thank you.
So what works really great is the texture. And if you use our infrared dots, we throw infrared dots to give reference points for those kind of points. So we have two ways of handling it.
Perfect. Thank you. Thank you very much.
Do you have issues with certain USB chips on the market? We've had problems with others. Yeah. So this is a big thing that we talk about on our website too. USB 3, we picked it because it's so common, right? The USB standard is well used and well known. Now we have a lot of people that it is a very tricky thing. They can't have the camera drop any frames. And what happens is if your connection's not good or you're using a less than qualified USB 3 cable, you can see data drops. So what we do is we recommend certain types of cable, really anything that says USB certified, because there's a specific certification they go through. There are many, many cables out there that are not USB certified. And it doesn't matter if it's on a mouse or a webcam. You don't care if a single frame drops or something like that. But it does matter when you're talking about the depth camera and you're using every frame to calculate distances. So that is one aspect. And another aspect is on PCs, even though there may be 4 or 6 or 8 different USB connections, they often use the same USB hub. So they're all drawing power and they're all sharing the same bus. So if you have 10 devices plugged into your same PC, you're probably not drawing enough power for the device if you have 2 or 3 or 4 cameras going on. So what we recommend is you get a powered hub, you plug it in, you make sure you secure it. We have secure bolts on the sides of our camera so that you can screw things in. It's easy to get a screw version of a USB, so it's tightly on. So if there's any movement or vibration, that cable's not coming loose, and you'll get better performance. Now, I said all that. The other thing that we're looking at is we're looking at trying to do different interfaces. That'll be something you'll want to look for us in the future, where we are going to explore other things like maybe Ethernet. Maybe we'll figure out Wi-Fi. Maybe we'll figure out 5G, and deal with the trade-offs. These are things that you should look for our future products at.
Ryan, we've got about 5 minutes left to wrap up. I was hoping, you might have a chance to show the Cerner, how they were using that. I know that was the example you had showed me where they were doing the skeletal to pull up and monitor patients in their bed. I don't know if you remember all that.
I wish I could, but it's on their proprietary equipment, and I cannot show it.
Okay,
But what I can do is, of course, one of the things that everybody should do is the Cerner patient observer. And it's an interesting, yeah, they have some videos on their site. I'm not going to bore you with having her talk, but essentially the idea behind it is I'm going to zone this person's body off with depth pieces. And then I'm going to define if his head moves to the left by 4 centimeters, I'm going to send an alert to a centralized station. Now this is an amazing thing for them because they can take one of our cameras, put it in the corner of the room, and they can monitor the whole room. They also love it because they don't have to do a ton of training. A person is a person is a person. You don't have to use a bunch of different AI models to make it work. Now they use AI with the data that we provide them, but we provide them with so much rich data, it makes that AI so much better than what it was. And this is a great example of where depth wins out over 2D. It just 2D can't keep up with a good depth camera here. Plenty of ways a 2D camera will work well, but there are specific use cases where that extra depth data is just remarkable.
Okay, that's good enough. As I said, it's kind of an interesting one given our given some of the different projects that we have going in our challenge. So I thought it was a good example.
The other things that may be interested, and you can look at these offline, is we try to get use cases. As more and more of these companies come out, we try to get them to do use cases for us, like the Segway Lumo able to do it, or Brain Corp, which does a, it's like an autonomous cleaner that you could like, think of the person driving around the big cleaner at the airport to clean the carpet. Well, Brain has designed something that uses our cameras and it's driverless and it just goes around and cleans. But these case studies are all very interesting. They have a lot of data. Simbi is one that I love because it's a robot that basically takes care of how to stock stores. So it scans all the shelves and says, you need 5 more cans of peas, and it sends it to a centralized place and it orders those 5 cans of peas, and then somebody can come out and stock that shelf specifically. But yeah, we try to put as many use cases we can do now, and then we keep adding more and more every day.
As I said, the skeletal and people tracking and the 3D scanning are probably pretty, and even the object measurement would be relevant for some of the stuff that we're doing and the challenge. With that though, unfortunately, we're at the end of the time because I've got our next session starts in 3 minutes. So I'm gonna have to wrap up unless there's any final quick question before we let Brian go. And well, Brian, with that, I thank you. I appreciate the time tonight, the presentation. I thought it was very interesting, and hopefully everybody got a lot out of it. And
thanks, Brian.
Thank you all for your time. Appreciate it. Thank you.
Thank you.